About another one of the value theorems. Today I want to talk about the mean value theorem. The mean value theorem. We've already the other two value theorems we've talked about have been the intermediate value theorem, which was quite a while ago, and then last time we talked about the extreme value theorem. Remember, the extreme value theorem says on a closed interval, if the domain is a closed interval, then the function has an absolute minimum and an absolute maximum. And actually, we're going to use that fact today when we're talking about the mean value theorem. Actually, the mean value theorem, which if you've had a good calculus class in high school, which I think most of you have, you may have heard of this before. But the mean value theorem, before we talk about that, I want to talk about a simpler thing based on a simpler idea, which is called Rolle's theorem. Rolle's theorem is named after this guy named Rolle. And Rolle was he was a French mathematician in the 1600s. During the time that calculus was beginning to become popular. It had just been sort of invented around this same time and was taking the world by storm. And actually, this is a strange fact. Rolle's theorem is is now regarded as one of the important foundations of calculus, which is why we're talking about it. But Rolle himself was kind of a calculus hater. He was like a calculus skeptic, and he made very, very public declarations that Isaac Newton and his techniques of calculus were all bogus. He said that the calculus was fundamentally flawed and led to wrong answers. He was wrong. Rolle was wrong about this, but it's a strange thing that he ended up also coming up with one of the fundamental theorems of calculus as we now know it. Anyway, here is Rolle's theorem. I think the story is other people realize that Rolle's theorem is important. Well, as you're about to see, it's very simple. This is the kind of thing that I think any one of us could have come up with this idea, if you really had to. I'll write it out in words first, and it won't seem terribly simple in words, but I'll draw a picture and then it will seem obvious. If f is differentiable on a closed interval a to b, say, and f of a equal f of b. So the function actually has the same y value at the two endpoints of the interval. Then there is some point in the middle, c, in the open interval a to b. So I'm just saying c is also in the domain, but it's not on the ends. It's on the inside somewhere, not on the endpoints. There's some c in the open interval a to b with f prime of c equals 0. The derivative at c is 0. All right? This is Rolle's theorem in words. Now, you should remember what Rolle's theorem says, although these words are not terribly memorable, in my opinion. The picture is much more easy to remember. And also, once we look at the picture, you will see why I said the idea is actually very simple, and it's something that any one of us could have come up with. It says, if I have a function here only defined from a to b, right? I'm only considering from a to b. And we assume that f of a equals f of b. That means the function on these two endpoints, it actually has the same y value here, right? And then it just does something else on the inside. So maybe it goes maybe like that. I don't know. It does whatever you want on the inside. It has to be differentiable. And what the theorem says, in this case, if the y values are the same on the two endpoints, then there's some point in the middle where the derivative is 0. I'm waiting. I just got an email, and it didn't ding. I'm pleased with that. Just so you know, I'm not constantly checking my emails during class. Sometimes it pops up. Yes, I was saying, can we see on the picture where is a point when the derivative is 0? Well, that would be a place on the graph where the slope is horizontal. I can actually see two such points, but maybe right there is one of them. F prime of c equals 0 right here. All right, and there's also another one, and it ends up at the same place where it started in terms of the y value. There has to be some point in the middle where the slope was horizontal. That's the only way this is going to work out, right? Not all that complicated. So, and I think the way the history goes about this with Roll is, this is something that Roll at one point wrote down somewhere, and probably many other people also realize this, but at some point, like in like 200 years later, people were going back in the history books and trying to determine who should be responsible for each of these like fundamental things in calculus. And it turned out, for whatever reason, they decided that Roll deserved the credit for this. At least one, maybe more than one, point in between where the slope is horizontal. All right. Roll's theorem is great. It's so great, I want to talk about why it's true. I'll use the P word. I'm not going to write down a super formalized proof, but it's worth talking about why Roll's theorem is true. I will just draw this picture again. This is the picture you want to have in mind your whole time. Demonstrate that there is at least one point inside the interval, in between, which has derivative 0. It's not very difficult. So I'm going to break this down into basically 3 different cases according to, I will say, this is slightly informal, but I'll tell you what I mean by this. Which way the curve starts out. All right, there are, I would say, 3 basic shapes that the curve could take, depending on where does it start going from the left side. It could, now this first case is very specific, but it could go straight across the whole time, absolutely straight across the whole time. Or it could go up first. That's what this picture does. It goes up at first. Or it could go down at first. All right, and those are really the only 2 sort of ordinary options. That first option is super particular, but it could either go up first or start off going down first. Or I suppose technically it could go straight across the whole time. All right, these are the only cases. I'm going to call these case 1, 2, and 3, and we will just talk very briefly. It's not hard in any case to say why there must be some point on the inside where the derivative is 0. All right? So case 1 is the simplest, the most particular. Case 1 so here the line or the curve, f of x, is always horizontal, right? It goes straight across the whole time. What do you say about a horizontal line? Are there any points on that line where the slope is 0? Yes, yeah, actually every point on the line has a slope 0. So in this case, obviously, there are points in there where the slope is 0, all right? This is sort of the stupid case because here the curve f of x is always horizontal. So in fact, all points have slope 0, all right? So this case is shown, right? Remember, in each case, I'm trying to demonstrate that there is at least one point that has a slope 0. This is kind of a stupid case in which all the points have slope 0. All right, what about case 2? This is more interesting. All right, in this case, the curve goes up from the left side. Remember these points, this point right here, this would be A to B, right? So in this case, we go up from f of A. So one thing I can say about that is that f of A is not the absolute maximum of this function, right? The left endpoint here, because the function starts by going up, the left endpoint is not the absolute maximum, all right? So f of A is not the absolute maximum, because the curve goes up from there. So wherever the absolute maximum is, it must be somewhere else, not at A, all right? And remember, there must be an absolute maximum on this interval, because it's a closed interval. By the extreme value theorem, there is an absolute maximum. But it's not on the left side, all right? The absolute maximum is also not on the right end. Anybody have an idea about this? How do we know the absolute value, the absolute maximum is also not on the right end? It's not on the left end just because in this case we assume that the curve starts by going up. Yeah? Yeah, right. Because the two ends have the same value. This is part of the setup of the Rolle's theorem. So the maximum does not occur on the left end, and it also does not occur on the right end, because f of A equals f of B. So f of A is not the absolute maximum. Also, f of B equals f of A. They're the same number, so f of B is also not the absolute maximum. Not the absolute maximum. All right? And what that means is we sort of ruled out both of the endpoints. The absolute maximum does not occur on the endpoints. That means it has to occur somewhere on the inside, and as we've said before, it must be at a point where the derivative is 0, right? That means it occurs not on the endpoints, it has to occur at a critical number on the inside of the interval, and such points have either derivative does not exist or the derivative equals 0, but we also assumed in the setup that the function is differentiable. So the derivative does exist everywhere. I'm going to try to say something like that. So the absolute maximum does not occur at the endpoints, so it must be at a critical number. So it's at some point C, where f prime of C is 0. And that C is not on the endpoints, because I already said it's not on the endpoints. All right? And that's the end in this case. So if the thing goes up to begin with, then that means the two endpoints are not the maximum, so the maximum is somewhere inside, and that must be the place where the derivative is 0. All right, and what if it goes down to begin with? I'm not going to write this all out because you say exactly the same stuff only about minimums, right? If the curve begins by going down, it means the left endpoint is not the minimum, and it means also the right endpoint is not the minimum because the two endpoints match. And so the minimum must occur somewhere on the inside, and it must be where the derivative is 0. So let me just say case 3 is the same, but with the word minimum instead of maximum. Right? And so in all cases, the derivative must equal 0 somewhere inside. This is Rolle's theorem. Anybody have any questions about that? It's a fairly, fairly obvious fact, in my opinion. Although it takes a certain type of. You don't have to be a genius to come up with Rolle's theorem. Maybe you have to be a genius to realize how important it is. That's the real achievement in a lot of these early mathematical theorems. All right? That's Rolle's theorem. Really what I want to get to today is called the mean value theorem. This one I'm not going to try to do the proof of, but it's based on Rolle's theorem, and I hope that you will believe me with the mean value theorem. There's a proof in the book. It's actually not hard to do. It's just a bunch of algebra, really, using Rolle's theorem. So the mean value theorem, this is a fancier version of Rolle's theorem. And the picture is very similar, which is why I don't think we need to go through the proof of the mean value theorem. It's basically the same picture, only sort of slanted. Here's what I mean by that. The picture for Rolle's theorem is this, something like that, and you find this point here where the slope is 0. Right? That's the Rolle's theorem picture. Rolle's theorem requires f of a equals f of b. The mean value theorem is the same idea, but it does not require that f of a equals f of b. And I would like to think of Rolle's theorem. I wasn't really thinking of it in this way before, but I'm going to draw some more lines here. If you sort of connect the dots here, nice little green line. These are Christmas colors. I should be doing Halloween colors. Sorry. This slope here also makes a horizontal, all right? Because f of a equals f of b, it means when I connect the two endpoints, I get a horizontal line. And the slope at that point in the middle is also a horizontal line, all right? The mean value theorem is like this, only it does not require that the two endpoints have the same value. So the mean value theorem is more like you just have two different values at the two ends. So this is, again, a to b. In the mean value theorem, you do not need any more requirements that the two endpoints have the same value. And the appropriate picture to think of in this case, so maybe my curve looks like that. The appropriate thing that the mean value theorem says is this. If I look at this slope here, which will not be horizontal, but it's just some slope, the mean value theorem says there exists a point in there which has that exact same slope. And on this picture, I would say it's around here somewhere. Not actually at the top of that hill, but close to the top, but not quite. The mean value theorem says there's a point in the middle where the slope at that specific point is equal to the overall slope of the connecting the two endpoints. All right, this is the mean value theorem. And I hope you'll agree with me, this is basically the same as Rolle's theorem if you kind of tilt your head sideways a little bit. All right, so the proof of the mean value theorem uses Rolle's theorem, but just tilts everything by a certain slope. And I hope you won't mind if we don't talk about the proof. Like I said, it's in the book if you really want to see the details. It's not all that inspiring in my opinion, because it's just the same at root. The main idea is Rolle's theorem, just tilted. All right. So let me just say what in words this means. It means that there is some point in the middle, C, in the open interval again, from A to B. This, again, it finds some point on the inside of this interval. So in this case, the C is right there. There is some C in the interval A to B where it's a little more complicated to say this. The derivative at C is equal to the slope of that dotted green line that I drew. And the slope of that line you could think of as the average slope from A to B, which we've talked about that in the sort of in the deep past. It's this, f of b minus f of a divided by b minus a. This is the average slope from A to B. Average slope from A to B. A to B. It's the slope of that dotted green line up there. All right? And this is also why it's called the mean value theorem. Mean as in average. It says that if you have any kind of function, it has to be differentiable. But if you look at the average about f of a equal f of b or anything, they could be anything. f of a and f of b. Then there is some c in the open interval, not one of the endpoints, with f prime of c, this is just what I wrote before, equal f of b minus f of a over b minus a. All right? And that fraction on the right, you should think of as being, it is the slope between the two endpoints of the interval. All right? All right, let me just, I'll drop a little mathematical verbiage here. This is called a generalization of Rolle's theorem. That's because it says, mean value theorem says more than Rolle's theorem. Like if you, for instance, if you look at this, if you only consider the situation when f of b does equal f of a, then this fraction becomes 0. And this whole thing says f prime of c equals 0, which is Rolle's theorem. So Rolle's theorem exists as just a special case of this one. Like this theorem here, the mean value theorem, is sort of, strictly speaking, better than Rolle's theorem. And anything you can demonstrate with Rolle's theorem can be demonstrated better with the mean value theorem. And the mean value theorem applies to many other situations that the Rolle's theorem does not apply to. I should have labeled this more clearly. This theorem right here, this is the mean value theorem. I think that was clear. I hope that was clear. This is the mean value theorem. All right. I want to do a couple examples of things you can do with the mean value theorem. You don't really use the mean value theorem to solve real world problems. You know, when does the rock hit the ground, or that kind of thing. But you can come up with interesting little sort of facts using the mean value theorem. Anyway, here's a very simple one, just to very basic demonstration. F of x equals x cubed minus 2x squared plus 3. And let's look at the interval minus 1 to 2. All right? I would just like to say, what does the mean value theorem say about this situation? Well, it says there exists a point in the middle, inside this interval, between -1 and 2, where the derivative equals something or other. So the mean value theorem says there is some c inside the interval -1 to 2 with f prime of c equals, remember what the theorem said, f of b minus f of a over b minus a. Can we figure out what exactly that is in this example? The b and the a are 2 and -1. Those are the endpoints of the interval. So f of b would be f of 2, which is, plugging into the formula right here, f of 2 is 2 cubed minus 2 times 2 squared plus 3. I believe that's just 3 because 2 cubed is 8, and 2 times 2 squared is also 8. So that's 3. And then the other side, f of a, is f of -1, which is -1 cubed minus 2 times -1 squared plus 3. And that is -1 minus 2 plus 3, which is 0. All right. So what the mean value theorem says, apparently, I'm just going to plug those numbers in. This is 3 minus 0 over 2 minus -1. That's 3 over 3, isn't it? Which is 1. So the mean value theorem says there's some point inside that range where the derivative is 1. So there's, I put the apostrophe in the wrong place. there's some point in the open interval, -1 to 2, where f prime of x equals 1. That's what the mean value theorem says in this example. Who cares about that is debatable. I mean, it's just sort of an obscure fact, I suppose, about this function. Although there are times in which this is very important. The mean value theorem is actually the basic idea behind the fundamental theorem of calculus, which is a super big deal that we'll get to by the end of the class. But at this level, it's just kind of a strange little obscure fact about this function. I think it's interesting. One thing that's very interesting about this is it allows you to say something about the derivative, even though I never used the derivative here. And this is makes it maybe a little bit believable that Roll, a calculus hater like Roll, could have come up with this, because I'm not actually doing the derivative at all. And on a certain level, I don't even need to do calculus at all to do this whole thing, right? Even if you didn't know how to find the derivative of a polynomial, for example, you can still come up with this conclusion. It's kind of interesting, all right? I want to talk about one other sort of, this I suppose counts as like a real world example. There is one type of situation in which I've seen the mean value theorem come up in the real world. Here's a very specific applied problem. Let's say I'm driving on the highway. The speed limit is, let's say, 65 miles per hour. And as I'm driving, I drive through a toll booth. I pass a toll booth, which is to say like an easy pass thing. People don't stop at toll booths anymore. I just drive through this thing at, let's say, 9:07 a.m. I tried to make some fairly realistic numbers. And then another toll booth, 4.4 miles later, at 9:11 a.m. And your job is to prove that I exceeded the speed limit at some point. Right? So what's kind of interesting about this is I never told you anything about my speed at any moment, all right? But you can still use the mean value theorem to deduce what my speed was at certain moments during my trip here, all right? Let's see if we can do it. So I want to think I have to translate this somehow into a function of some sort. So I'm going to say I'll call it like f of t be the distance traveled at time, and I'll say at t minutes after, how about t minutes after 9 a.m.? I want them to be ordinary numbers, not times. The distance traveled at t minutes after 9 a.m. So I have, the road is like here, and then let's say here's my two toll booths, the easy pass thing that I've got to drive under, right? And I said the second one is 4.4 miles past the first one. So in terms of distances, I'm just going to call this distance 0, and I'll call this distance 4.4, right? You might as well choose the numbers so that you start at 0. And so the information that I've given here, I pass one toll booth at 9:07 a.m. So 9:07 a.m. This means that f of, I'll just say 7, is 0. Because I'm counting the times in terms of minutes after 9 a.m. So the time that I passed that first toll booth is time 7. And my distance it counts as 0, because I'm calling this distance 0. And then I pass another toll booth 4.4 miles later at 9:11. How would I write that in terms of another, another f of something equals something? Yeah, f of 11 equals 4.4. My distance in minute 11 after 9 a.m. was 4.4 miles. All right. Since I have two values of the function, we have a setup where I can use the mean value theorem. Right. All you need is the f of v and the f of a, and that's what I can use for these 2 points here. So I'm going to use the mean value theorem on the interval a to b will be, in this case, 7 to 11, right? Those are my 2 endpoint, the times at the 2 endpoints. So it says there is some point C where f prime of C equals this stuff, f of b. I'm just writing the mean value theorem again. F of b minus f of a over b minus a, which is, in this example, f of 11 is 4.4 minus f of 7, which is 0, divided by b minus a, that would be 11 minus 7, right? That on the bottom is 4, so this is 4.4 divided by 4, I guess, is 1.1. Look at that. Simplifying decimals inside fractions. Can you believe it? All right? So there is a point at which f prime of c is 1.1. What's the meaning of this in terms of the scenario that I'm describing here? It's not a critical point, because critical point would mean the derivative is 0. Here it's something else. It's 1.1. Can anyone say, first of all, just in general, what does this mean, f prime of c, in terms of my scenario here about the car driving? Yeah, it's the slope. What does that mean in terms of the car? Yeah, this is the velocity of the car at a certain point, is 1.1. But the units, though, is a little weird. It's going to be, just because of the way everything is working out here, the time units are minutes and the distances are miles, right? So the units here, what this means is, so at some time, I don't know when, but at some time, like this c, the mean value theorem doesn't tell you when the time is, but anyway, at some time, my speed was 1.1 miles per minute. And this, really I'm interested in miles per hour. So to convert this to miles per hour, you would multiply by 60, and you get 66 miles per hour. And there, I have demonstrated, remember our job in this problem is to demonstrate that we exceeded the speed limit. And I said the speed limit was 65. There must have been a moment at which we were going 66. Busted! Right? There was a moment when we were exceeding the speed limit. This doesn't tell you when you were exceeding the speed limit, and let's be honest, there probably were times when I was going even faster than that, but the mean value theorem doesn't tell you that. It just says that there was one moment at which you were going this fast. In fact, that speed, 66, would have been my average speed during that whole time. That's what the mean value theorem is all about. So my average speed was 66. The mean value theorem says, actually, that means there must have been a particular point at which you were actually going 66. Probably sometimes you were going faster and sometimes you were going slower. All right? Any thoughts about this? This is actually, this exact example, I made up the numbers, but this exact thing, it has been at times sort of a controversial legal matter. I don't know about, I know of a specific legal case in England where there were sort of 2 checkpoints, and they did something exactly like this, where they measured a car at one thing and then how long it took for the car to get to the next thing. And they did a little mean value theorem magic to prove that the car must have been driving faster than the speed limit at some time in the middle. And apparently the guy went to contested the ticket or whatever, and he said, it doesn't work that way, governor, whatever, in England. He said, if you want to give me a ticket, the police has to actually observe me violating the law. And they didn't. They didn't see me going faster than the speed limit. All they did was somehow, some kind of abstract theoretical proof that I was going faster. But in order to give me a ticket, you need to actually observe me going faster. It's not good enough to give me some kind of mathematical proof. I don't actually know what happened to this. But this is a controversial idea, legally speaking. And people, I've heard this discussed actually in the great state of Connecticut. I don't know if you're up with like Connecticut politics, but something I believe our governor, Ned Lamont, wants to install toll booths on 95, like right by campus here. And somebody asked him, are you going to start handing out speeding tickets based on the Easy Pass data? Because they can tell if you go through one toll booth and then go through the next one, just like this. They can tell if you were speeding or not based on that. And they asked Ned, how do I know this isn't just some kind of elaborate speed trap proposal? And Ned's reassuring answer was, I promise we won't do that. Which to me is not all that reassuring. But it's true, like whenever you drive through these Easy Pass gates, they could very easily hand out speeding tickets to people based on that data. And I think they don't just because they don't, not because they can't. It's a strange situation we're in. Got someday they'll change their mind and start giving us tickets. All right, this is the mean value theorem. We got some time left. Two more interesting things to say based on the mean value theorem, and then we'll go on to the next section here. So, two more fun facts. Fun fact based on the mean value theorem. I'm going to write this like a theorem. She doesn't like fun facts, I know. Sorry, she told me she had to leave. I'll write this as a theorem. It's not all that complicated, though. It says if f prime of x equals 0 always, then what can you say? This is probably something that everybody knows. What can you say about a function if your function, its derivative, is always 0 at every point? Well, what do you know about that function then? You ever heard of a function whose derivative is always 0? It's horizontal. I was going to say as like a formula for such a function, it's a constant, right? It's just if I say the derivative is 0 always, then I'm going to say f of x is a constant function. I don't know if you ever thought about this, but this is actually not so easy to demonstrate. So everybody knows that the derivative of a constant is 0, right? But that doesn't necessarily mean that the only thing whose derivative is 0 is a constant, right? This theorem here is saying kind of the other way around. If the derivative is 0, the only way that's possible is for your function to be a constant. Like there is no other weird kind of function whose derivative is always 0. If the derivative is always 0, it must be a constant function. This actually you can demonstrate using the mean value theorem. I want to consider this. So we're going to consider my function like this. It has a closed interval, as always, from a to b. And it could do whatever you like, a to b, right? I would like to consider some other point. Just go from a to some other value x here. So I'm going to consider the mean value theorem on the interval from a only to x, not all the way across to b, but just over to some other point. This is trying to justify that, what I wrote as a theorem. I guess this is a proof, well, it's not going to be super technical. What does the mean value theorem say? It would say some point exists, f prime of c, where it equals f of what is it? F of x minus f of a divided by x minus a, right? This is what the mean value theorem would say if I only considered the interval from a up to just some other point x, right? But I said I'm trying to talk about the situation when f prime is always 0, all right? So in this example, if f prime of c is always 0, that means, I'll just say, but f prime of c must be 0. So what does that mean? It means f of x, 0 equals f of x minus f of a over x minus a. You can multiply that denominator onto the other side, and it will just multiply times the 0, and it'll stay 0 on the other side. So 0 equals f of x minus f of a. So that means f of x equals f of a, and this is for every x inside the interval a to b, all right? What we've just demonstrated is that, like all these intermediate points, they all have to be the same y value as f of a. And that means that the function is a constant, right? All the points in between have to end up equaling the one on the left. So all the values here, all the y values, they must be the same as f of a. So all values are equal to f of a. And only, that means that the function is a constant. It has only one y value, f of a. Right? That's it. They're all the same. So f is a constant. All right? It's because of the mean value theorem that you get this. It means the derivative of a constant is 0. Everybody knows that. This means if the derivative is 0, it must have been a constant. Another way to say that is the only function whose derivative is 0 is a constant. All right? I said I had 2 fun facts. That was the first one. The second one is even simpler, but this actually you may recognize as being important. So this is fun fact number 2. I'm going to say this is a corollary. That's a fancy word for like another theorem which follows immediately using the one we just did. So a corollary of this is that if f prime of x equals g prime of x, then f of x is equal to g of x plus c for some constant. This is less obvious and more important. It says if 2 functions have the same derivative, then they must be the same function except maybe with a constant added on to the end. All right? This, if you've ever done the integral before, you know that this is important. This is why when you do the integral, you always get like a plus c. I don't know if that means anything to you, but you've seen that integration constant plus c before. It's because of this. If you have 2 functions and their derivatives equal each other, then the original 2 functions must be the same except for possibly differ by a constant. All right? And why is this true? It follows from what I said before. So if f prime of x equals g prime of x, then you can move this around. It'll say f prime of x minus g prime of x equals 0, which means the derivatives of f of x and g of x, f prime minus g prime is 0, so that means f of x minus g of x is a constant. Because what we just said, the first fun fact was if the derivative is always 0, then that function is a constant. And here, this says the derivative of f minus g is always 0, which means f minus g must be a constant. And what does that mean? That means this, right? If you rearrange things. So f of x minus g of x is some constant c, and that means f of x equals g of x plus c. Right? If 2 functions have the same derivative, then they are equal to each other, except for plus a constant. All right. This is true, by the way, only for differentiable functions. Right. There are some weird examples where the function is not differentiable, where this is not quite true. I'm talking about differentiable functions. All right. these are all the fun facts that I had concerning the mean value theorem. Any thoughts about the mean value theorem? It's important, although mostly for theoretical reasons, and we are going to mention the mean value theorem a couple more times later in the semester, although it's not really to do homework problems using the mean value theorem, because it gives you only very specific and weird kind of information. But it is important from an abstract point of view. All right, great. We got a little bit of time. I can give you a little intro to the next section. That's the end of this section about the mean value theorem. The next part in the book is about derivatives. This is very down to earth, I think. Derivatives and the shape of the graph. This is something that we've mentioned, here and there, and probably everything that I'm about to say for the next 10 minutes is going to be fairly obvious, but it's worth saying. So there are actually several different types of shapes that we're going to try and identify by looking at graphs and talk about what the relationship is with the derivative. But the most basic sort of connection between the derivative and the shape of the graph is increasing versus decreasing. Increasing versus decreasing. And what does that have to do with the derivative? This is a simple idea. So increasing, what I mean by that is like it goes up as you go to the right. This is increasing. Right? It means up as we go right. And decreasing is going down as you go to the right. Something like this, right? That is decreasing. Going down as you go to the right. Make sure you always consider the picture from left to right when you talk about increasing versus decreasing. This is down as we go to the right. And what does this have to do with the derivative? Well, the derivative represents the slopes, and in an increasing function, the slopes are always positive, right? If you were to draw these tangent lines, they would always be going up. Versus in a decreasing function, the slopes are always negative. So increasing means f prime of x is positive, greater than 0, and decreasing means it's negative. Right? And a typical function is not going to be just one or the other. Usually a function has portions which are increasing and portions which are decreasing. So a typical example might look like, how about that, and then it comes down to there, and it goes go back up. Something like that. This function is sometimes increasing and sometimes decreasing. And a basic question I could ask you is, on which intervals of x values is it increasing or decreasing, right? You want to say on this interval it's increasing, on this interval it's decreasing, somewhere else it's increasing. What do you think? Can anyone say what's an interval where it's decreasing? It's decreasing on, I'm always going to write these as open intervals. What do you say? X values where it's decreasing? Zero to 2, yeah, thank you. This is not a trick question, right? It's decreasing like here, right, along this part of the curve. Or if I ask you just about the x values there, it's 0 to 2. So the interval 0 to 2. And where is it increasing? Well, it's increasing everywhere else. So to the right side, I would say from 2 to infinity. Increasing on the interval from 2 to the infinity. And also on the left side, I would write that as minus infinity to 0. Right? That's the two sides on the ends. How could we determine this using an equation rather than looking at the picture? Looking at the picture is easy to do, but how could we determine just by looking at the equation? Well, it has to do with those critical numbers. In this picture, the critical numbers would be here and here. And it's not a coincidence. The critical numbers are these same numbers which ended up being the interval endpoints. They're 0 and 2. All right? So to answer this same question, even without looking at the picture, you can do it by finding the critical numbers and then doing a bunch of critical number action to decide decreasing versus increasing. This is what we're going to do for our next, major kind of thing to talk about doing. Maybe we'll start that next time. It's easy on a picture. It's a little more involved with equations. I think that'll do it. Right? Have a good Halloween. Stay safe out there.
I got the first one right, and then for the second one, I just didn't